So you do some more quick conversion, and you find out that when Mario's big, he jumps 5.25 meters, but when he's little, he jumps 6.3 meters. And then you think of Luigi, and you look at Luigi when he's big, and he jumps even farther than Mario. He jumps 5.95 meters. But when they're small, they jump the same, so he jumps 6.3 meters too. So then you want to know, how much work is that? So, you take 76 times 9.8, because that's what gravity is, and you get 744.8 newtons, which is how much Mario weighs in newtons. And then you take that, because you know that work is force times distance. So you take that force, and you multiply it by the distance. And sometimes you mess up writing, because you're not very good at writing. And this time you're going to do Mario. So at the end of it, Mario ends up doing 3,910.2 joules of work, because a joule is a Newton meter squared. Meter per second squared. And then you wonder how much work Luigi does when he's all powered up and stuff. So you take 76 again, and you multiply it by 9.8 again, and you still come up with 744.8 newtons. But then you have to multiply that by 5.95, which is considerably more space. And you come up with even more work, 4,431.6 joules of work. So obviously Mario is working a lot less than Luigi, just relying on his brother for everything. So then you try and do it with wondering how much it would take if they were little. And it doesn't really matter who you pick for this one. So you take 38 and you multiply it by 9.8, because that's what gravity is. And you should come up with 372.4. And then you have to multiply 372.4 by how far they both jump, which is 6.3. So when they're little, they both do the same amount of work, and it still ends up to be 2,346.1 joules. Which is a lot, but it's almost half as much as Luigi does, and like two-thirds of what Mario does. But at least they're doing the same amount of work this time. It's equal. So what if you fiddle with gravity? I mean, it takes them a long time to jump across that screen. It takes a whole, 3 seconds. So maybe you can make gravity 8.9, because that's a good number. You're just flipping some numbers around. So you take a big one, let's say it's Mario, and you multiply that by 8.9 to get the new force. And you write 8, because you have no idea what you're doing. There we go. And when you multiply that by 8.9, you come up with 676.4 newtons, if Newton lived on some planet where 8.9 was gravity. And then you multiply that force, 676.4, times the same distance, which is going to be 525. So if we lived on whatever the planet is that Mario and Luigi live on, where they have giant mutant mushroom wereshroom things walking around, then we would have to work with 4,024.6 joules of work just to kill these things in our backyards all the time. Although for Mario and Luigi it isn't such a bad plan. And what if you got small? What if you ran out of power-ups? Then you would have to be 38. And you would have to multiply that by 8.9, because in some whatever world this is, that's gravity. And you come up with 372.4 joules, or newtons of force. And then you have to multiply that by the distance, which is still going to be 6.3, even though you live on whatever planet it is that you live on where 8.9 is gravity. And then you have 2,346.1 joules of work. So it's a little less work. I mean, not a lot less work, but a little less work. So maybe you can use this to help you beat those Goombas in the boss level, and maybe you can use it to try and get ahead in Assassin's Creed, because now you know how far you have to jump in it, how easy it is for you to do that, and oh wait, teacher's coming.